So we can use these relationships now that we've just developed to solve for unknowns. So in determining an unknown parallel resistor, sometimes you need to determine the values of the resistors that are to be combined to produce a desired total resistance. For example, you use two parallel resistors to obtain a known total resistance. If you know or arbitrarily choose one of the resistor values, you can calculate the second resistor value using equation 6-3 for two parallel resistors. So let's take a look at how we develop this. So we're going to start with our reciprocal relationship for the total resistance. And instead of calling them R1 and R2, we're going to call it RA, which is our known resistance, and Rx, which is the resistance that we want to solve for. So let's now move our terms around so that we have Rx on the left side of the equation like we normally do. So we have 1 over Rx is equal to 1 over the total resistance, now minus the known resistance value A. So let's cross multiply so that we can get a common denominator. And when we do that, we have RA minus R total divided by R sub A times R total. Now when we invert that value one more time, both sides, we have the unknown value of R sub X is equal to the product over the difference, or minus the sum, however you want to look at it. It's still the product over the sum, but now it's a difference. So R sub X then becomes the unknown resistor, and R sub A is the known or selected value. So how do we do this? So let's take a look at using that relationship. Again, this should be a relationship you're keeping track of, writing it down in your notebook. Suppose that you wish to obtain resistance as close to 150 ohms as possible by combining two resistors in parallel. Why would we do this? Well, sometimes you may need to make a repair. You may need to replace a resistance in a circuit, and you may not have the exact resistance that you're removing. So you may have a bench stock, or you may have some spare resistors laying around that you could lash together in parallel and get close to the resistance of interest. So there's a 330 ohm resistor available. What other value do we need? So we're going to start with our 330 because we know when we tie two of them together, it's going to be smaller than the smallest. So we have a total resistance of 150 that we need to get to. And our known value is 330 ohms that we pulled out of the bin or out of our bench stock. So now if we place those values into the relationship, the product over the difference, we have 330 ohms times 150 ohms, and the difference of 330 minus 150 gives us 275 ohms. So the closest standard value would be 270 ohms if you were to have that value in your bench stock, or if you were able to purchase one. So again, with the related problems, go ahead and do this one on your own. Improve your skills. Make sure you understand what's going on here. Notation for parallel resistors. Okay, this is just a simple way of writing down, instead of writing down all of those long equations, those inverse relationships. If I know I have R1, R2, R3, R4, and I5 are all in parallel, I can use this notation, the two parallel bars in between each one. And it's telling me that all of these are in parallel. So if I had two resistors, a 10k ohm and a 5k ohm, and they were in parallel with each other, I could simply write down 10k ohms in parallel with 5k ohms. Now you'd still have to do the math to calculate what that value is, but this is just a shorthand notation that allows you to keep track and write down what in fact you're looking at here. So now let's get back to Ohm's law and its applications in parallel resistive circuits. So we're going to apply Ohm's law in a parallel circuit to find the total current, find the current in each branch, the voltage across the parallel circuit, and the resistance. So in this example, you can see we've got two resistors that are in parallel. Don't let the little ground symbols throw you. R1 and R2 are in fact in parallel with each other. So let's determine the total current produced by the battery in this case. So we don't know anything about the branch currents, so we need to determine what the total current is by finding the total resistance over here. So the first thing we're going to do is we're going to calculate the total resistance using the product over the sum. And we end up with 100K times 56K divided by the sum of 100K and 56K, which gives us 156K. Divide that into 56,000 K ohms squared, and we get a value of 39.9 K ohms. So that's the total resistance of these two. Again, check it. Is it smaller than the smallest? Well, 56 was the smallest. This is smaller. So now, given a battery voltage, our source voltage of 100 volts, we can stick the value back into Ohm's law for I total. V source by R total then gives us 100 by 35.9 K, or 2.79, 2.8 milliamps of total current. Now, if we wanted to, we could use that 2.79 to determine how much of it is going through R1 and how much of it is going through R2. So, in fact, the related problem asks you to do that. So go ahead and do that. Determine the current through each resistor of the parallel circuit. So again, I've got three different resistors, three different values: 1K, 2.2K, 560 ohms. So what I can do first is I can calculate, since I know the voltage drop across each of those resistors is the same, it's V source. I can calculate each of the individual currents, I1, I2, and I3, by using V source over the resistor in question. So 20 volts over 1K, 20 milliamps. 20 volts over 2.2K, 9.09 milliamps. 20 volts over 560 ohms, 35.7 milliamps. So now I know at this first node, where I total is going into that first node, that the sum of these three currents will be I total. And you can go ahead and do that. Okay? Something that's in your text here says use multisim. I hope you're using multisim in your lab to solve for some of these. CSN, does have student copies of this available. Check with your lab instructor to find out how you can get a copy of multisim so that you can do some of these things using simulations. Find the voltage source across the parallel circuit. So again, now this one, I've got three resistors, 220, 560, 1K, and an unknown source, but I do have a known IT, total current. So what do I need to do to determine what V source is from these three? Well, I do know one thing just by looking. I know that always in this case where I have these three resistors, that the drop is going to be the same. The thing that will change is the current through each of them. So if I go back to the relationship of total resistance being equal to 1 over the total sum of the conductances, and I know I can inverse each of those relationships from G to R, then plug the values in for R1, R2, and R3, 220, 560, 1K ohm. When I get those values, then I can sum them, which gives me now my values in Siemens or millisiemens. I can sum them together. I get 743 millisiemens. Now I invert this one more time, and I get 136 ohms. So now I know the total current. Is it smaller than the smallest? Well, 220 ohms was the smallest. 136 is smaller. I can put that back into the relationship. V sub S, the source, is equal to the total current times the total resistance, 10 milliamps, 136 ohms, to give me 1.36 volts. So that's our source voltage, 1.36. Sometimes a direct measurement of resistance is not practical. For example, tungsten filament bulbs get hot after turning them on, causing the resistance to increase. An ohm meter can only measure cold resistance. Assume you want to know the equivalent hot resistance of the two headlight bulbs and two tail light bulbs in your car. The two headlights normally operate at 12.5 volts or 12.6 volts and draw 2.8 amps each when they are on. So what's the total equivalent hot resistance when the two headlights are on? And assume the total current for the headlights and tail lights is 8 amps. That's a lot of current. If you're not becoming familiar with that, 8 amps is a lot of current. You figure most of your house circuits in your home are 15 amps. Well, that's a little more than half of that. When all four bulbs are on, what is the equivalent resistance of each tail light? So if I use Ohm's law to calculate the equivalent resistance for one headlight, R sub head, is equal to V over I, then I'm able to come up with a resistance of 4.5 ohms. Because the two bulbs are in parallel and have equal resistances, then I can divide that in half to get half of the headlight values, the resistance. So 2 into 4.5 gives me 2.25 ohms of resistance. Okay, so that's our resistance. Use Ohm's law to find the total resistance with two headlights and two headlights and two tail lights on. So we're going to sum the headlights and the tail lights together to get R sub T, head plus tail, which gives us 12.6 volts and 8 amps of current. So that total resistance, headlight and tail light, is 1.58 ohms. Apply the formula for parallel resistors to find the resistance then of the two tail lights together. Okay, so we're going to lash these together and determine using the parallel relationship. So 1 over the total is equal to 1 over the total headlights plus 1 over the total tail lights. So in doing this, 1 over the total tail lights then will equal 1 over the total headlights plus the tail lights minus, we're going to subtract it out, the total for the headlights, and we come up with 1 over 1.58 minus 1 over 2.25, which gives us, and when we invert it, a total tail light resistance of 5.25. So the two tail lights are in parallel, so each light has a resistance of 2 times 5.25 or 10.5 ohms. Okay? So a little practical example. So when we come back, we're going to look at sources in parallel and how do we treat them in a parallel circuit.